Hello everyone. In this video, I'm going to go through Lyapunov indirect method and linking Lyapunov to linear quadratic regulator. A Lyapunov function is a scalar function defined on a phase space which can be used to prove the stability of an equilibrium point. The Lyapunov method is applied to study the stability of various differential equations and systems. One can think of the Lyapunov function as a generalization of the idea of energy of a system. Then the method studies stability by looking at the rate of change of this measure of energy. Various types of stability may be discussed for the solutions of differential equations describing dynamical systems. The most important type is that concerning the stability of solutions near to a point of equilibrium. This is discussed by the theory of Lyapunov, which is indirect method of Lyapunov, also known as linearization method. For finding the stability of a nonlinear function, first we consider the system x dot equal to function of x and t. First we linearize the system and then set it to equilibrium point. If the linear system is stable, that is real parts of eigenvalue is on left hand plane, then the nonlinear system is locally asymptotically stable. If one or more real parts of eigenvalue is on right hand plane, then the nonlinear system is not locally asymptotically stable. Consider this as a system trajectory where xe is the equilibrium point and x naught is a point very close to the equilibrium point. If all solutions of the dynamical system that start out near equilibrium point stay near it forever, then xe is Lyapunov stable. A more stronger condition is if xe is Lyapunov stable and all solutions that start out near xe converge to it, then xe is asymptotically stable. Let's consider the pendulum example, which originally motivated the invention of the Lyapunov function concept. At time equal to 0, with no force applied on the pendulum, it will sit perfectly vertical. That position is called equilibrium, which is the position at which the forces acting on the bob are perfectly balanced. This point is stable. If some force is applied to the pendulum, over some time it would come to a stop due to the friction. Then this point is called asymptotically stable. The equation of motion comes from the Newton laws, but they are non-linear in this case. Since energy is constantly dissipated by the system, mechanical energy serves as a suitable Lyapunov function. The equations for a pendulum with friction is x1 dash equal to x2 and x2 dash equal to minus x2 minus sine x1. Here g by L and k by L are considered to be equal to 1, where g is the gravitational acceleration, k frictional constant and L the length of the pendulum. For simplicity of notation, we assume that the equilibrium point to be tested for stability is the origin. Taking the differential equation of the function with respect to x1 and x2 will give us the matrix A value. Now we try to find the stability of the system in MATLAB. First we enter the values of matrix A and Q, which is positive definite. Then using command x equal to lib A comma Q solves the Lyapunov equation whose eigenvalues are in K. Using the if-else condition along with the relational operator, we will see whether the system is stable or not. For the above system with equilibrium point at origin, we get the Lyapunov solutions and its eigenvalues. From it, we can infer that the system is positive definite and hence stable. The above method is very popular because it is easy to apply and it works well for most systems. All we need to do is to be able to evaluate partial derivatives. The major drawback, however, is that since it involves linearization, it is applied for situations when the initial conditions are close to the equilibrium. The method provides no indication as to how close is close, which may be extremely important in practical applications. Linking Lyapunov function with linear quadratic regulator. Here we are interested in the integral quadratic performance measure for any fixed equilibrium point of a system. That is, the Lyapunov function v serves as an upper bound on the integral quadratic cost. The Lyapunov function v of x equals to x transpose p x. Here p is symmetric positive definite matrix. For the Lyapunov function, if v of x is greater than 0 and v dash of x is less than 0, that is when the system is considered to be globally stable. The original Lyapunov theorem only gives a sufficient condition. That is, if we start with P and solve for Q, the condition of the test may or may not work, while if we start with Q and derive P, the condition is necessary and sufficient. These are the references used for this project. Thank you.